I keep saying that modular arithmetic is a new number system, that we're creating a new number system, and that you might remember I said some time ago that we're trying to keep everything in the integers. We're trying to express everything in terms of integers. Everything has been expressed in terms of multiplication, subtraction, addition, keeping it in the integers. So we're going to define a new set based on all the theory we've built up to now. If we take this set of integers from 0 to n minus 1, we can call that the set of integers modulo n, and here's the notation we use. We pronounce it z mod n. We can define addition and multiplication on this set. Basically what we do is we just add the two integers and then mod them, reduce them mod n. Same with multiplication. Okay? And because this is an operation, we can make an addition table, we can make a multiplication table. We're going to look at some examples of these right now. So let's first take a look at addition and multiplication tables for z mod 6. Remember, I pronounced this z mod 6. So the addition in z mod 6, I'm just going to pick a random spot on this table and have us kind of think out loud about why it is what it is. So like, let's say this right here. This is saying 3 plus 5 is 2. Why is 3 plus 5 equal to 2? Well, 3 plus 5 is 8, but 8 mod 6 is 2. Let's pick another one. What about this here? 5 plus 3, which is 8, is 2. Because 5 plus 3 is 8, 8 mod 6 is 2. We're in the mod 6 world here. You might notice some interesting patterns with the addition table. You might notice certain patterns as to where the numbers are appearing. Multiplication is pretty interesting though. So let's look at what's going on with multiplication for z mod 6. Well, 0 times anything is 0, so it's no surprise that this row and this column are all zeros. But what other places do we see zeros? We see 0 here, 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 and here. That's kind of crazy. 3 times 2 is 0 in the mod 6 world. Why is that? Well, 3 times 2 is 6. 6 mod 6 is 0, right? Similarly, 4 times 3 is 12. 12 mod 6 is 0. Another interesting thing is there's a couple of places where there's a 1. So there's no surprise that 1 times 1 is 1, but 5 times 5 is also 1? What is going on there? 5 times 5 is 25. 25 mod 6, we can calculate that in our head pretty quickly. Remember, I can subtract a convenient multiple of 6 from 25. I'm going to pick 24. So 25 minus 24, that gives me a 1. The mental math you practiced in the previous examples is going to help you do calculations in modular arithmetic. So we have a crazy situation here. We have two non-zero elements multiplying together to make 0. In the real numbers world, we don't ever allow two non-zero numbers to multiply together to get 0. The only way two numbers could multiply together to get 0 is if one or both of them are 0. And that's like the basis for solving all of our equations and everything. So this is kind of crazy if you think about it. What about z mod 7? Again, not you know, very similar patterns to Z mod 6 for the addition table. Let's focus more on the multiplication table. Again, there's the 0 column and the 0 row. But notice there's like a bunch of places where we see ones. In fact, I have exactly 1 in each row. In fact, this is kind of like a Sudoku board. Every number 1 through 6 is appearing exactly once in some way. There's other cool patterns you could observe and notice. I'll let you think about that. But for example, you could do 5 times 3 and get 1. 5 times 3 is 15. Take away a convenient multiple of 7, since we're in the mod 7 world. I'll pick 14. 15 minus 14 gives me 1. And there's other pairs of numbers that have that too. 2 times 4 is also 1, which is kind of crazy if you think about it. We're going to talk about this more in a moment, but I want to just emphasize a couple of things. So like this 2 times 4 is 1. If 2 times 4, I'll use this circle times, 2 times 4 is 1, that's kind of like saying 2 to the negative first power is 4. If you say 5 times 3 is 1, 5 times 3 is 1, it's like you're saying 5 inverse, 5 to the negative first power is equal to 3. We don't allow negative exponents for integers usually, because a negative exponent on an integer will, in almost all cases, give us a fraction. And once we get something that's a fraction, that's not an integer anymore, like, 1/5, if we think of this as 1/5, 1/5 is not an integer anymore. But the cool thing here with modular arithmetic is I can figure out something to multiply by 5 to get 1. So notice, typically in the real number world, if I do 5 times something and get 1, that something has to be 1/5. There's no other possibility. We refer to 1/5 as the multiplicative inverse of 5. That's the formal number for, or the formal way of saying the number you multiply by 5 to get 1. Okay? But in modular arithmetic, sometimes there's a way to multiply an integer by another integer and get 1. In other words, sometimes you have an integer multiplicative inverse. And when I say integer, I mean it in like integer in quotes, because these are integers modulo something. So just to reiterate, there were some key differences between the multiplication tables for Z mod 7 and Z mod 6. One thing that I didn't mention about Z mod 6 that we talked about in Z mod 7, notice in Z mod 6 we don't have this nice property where that's like a Sudoku board, right? Yeah, here I have 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. But look here, in these rows, not all of 1 through 5 are represented. But in this one, they are. We're going to talk about some properties of these operations that we defined on the integers mod n. That's the circle plus and the circle times. Both of these operations are commutative, associative, and combining them together, they satisfy the distributive laws that we're used to with integers, or real numbers, in fact. So all of these properties hold true. 0 is always going to be an element of Z mod n. We call that the additive identity because when you add 0 to something, it's not going to change it. It keeps it the same. For every A in Z mod n, there's a unique integer that you can add to it to get 0. That's the additive inverse. So just taking a quick peek back at the table, what is the additive, notice I'm saying additive, not multiplicative right now, what is the additive inverse of 4 mod 6? Well, I need to find the number that I add to 4 to get 0, so that's 2. 2 is the additive inverse of 4. Usually in the real number world we say the additive inverse of 4 is negative 4, but there's no such thing as negative 4. We're only limited to 0 through 5 because we're in the Z mod 6 world. So that's additive inverse. That's going to be true here. One more thing. 1 is going to be in any of these, because remember n is greater than or equal to 2, which means you always have at least 0 and 1. So 1 is called the multiplicative identity because when you multiply by 1, the number doesn't change. Okay? So these first 6 properties are going to hold true for Z mod n for any n greater than or equal to 2. Now, the thing that made Z mod 7 special was this last one here, number 7. So for every integer in Z mod n star, in other words, for every non-zero element of Z mod n, there's a unique non-zero integer a in Z mod n such that a times a prime is 1. So this big warning, this one here is only true if and only if n is prime. Okay. And as I was saying informally before, we call that the multiplicative inverse or reciprocal, even though we don't have fractions here. And we write it a to the negative first power. Even though we don't technically allow negative exponents for integers, we do now because in some cases there's a multiplicative inverse which we indicate with an exponent of negative 1. So we're going to look back at the tables for Z mod 6 and Z mod 7 to consider the next example. So from the tables above, only 1 and 5 have multiplicative inverses in Z mod 6. We kind of talked about that already. 5 times 5 is 1. Remember, actually, 5 in Z mod 6, 5 is like negative 1. So it kind of makes sense that negative 1 times negative 1 should be 1. That's a pretty convenient thing to remember when you're doing these calculations. In Z mod 7, every non-zero element has a multiplicative inverse, and here's the list of the multiplicative inverses. You should verify these by doing the multiplications and doing the mental math to kick the product down to 1. So quick note about algebraic structure. The axioms that were listed over here in the corner, including number 7, if a set has these properties, we call that set a field. And examples of fields include the real numbers and the rational numbers. Both of those are actually infinitely large fields. But Z mod n, when n is prime, is an example of what's called a finite field. And you can study about that more in an abstract algebra class or a number theory class. It's a pretty cool fact that you can have a field that's not infinite in size.